Hello and welcome to today's lesson on Scalars and Vectors, which is part of the Forces topic in GCSE Combined Science Physics. So in today's lesson we're going to look at understanding what scalars and vectors are. So if we've been successful and learnt in today's lesson, we should be able to describe the differences between scalars and vectors, be able to add vector and scalar values, and finally draw vector diagrams for vectors where the size and the direction of the arrow represents the size and the direction of the vector. Now this links into the following part of the GCSE Combined Science Physics specification 6.5.1.1 Scalar and Vector Quantities. Now scalars are quantities which only have a magnitude or a size associated with them. Now this includes the following quantities, things like mass, temperature, length, energy, time. Now all of these quantities have a magnitude, but they don't have a direction they act in, they just exist. Now vectors are quantities which have a magnitude, a size, and a direction associated with them, and these could include things like weight, acceleration, momentum, velocity, and force. Now all these quantities have a magnitude and a direction they act in. So let's just clarify that. Scalars are quantities which only have a magnitude associated with them. Vectors are quantities which have a magnitude and a direction associated with them. Now we've got to treat these concepts differently both conceptually and mathematically. Now some quantities have a scalar and vector counterpart. Now in these examples the vector is the scalar with the direction added to it. So examples include speed being the scalar and velocity being the vector, and distance travelled being the scalar and displacement being the vector. So vectors are scalar values with the direction included in their answer. Now the easiest way to add a direction is to place either a plus or a negative value in front of the number. Now so for example, plus 20 meters per second and minus 20 meters per second show that the object is moving in opposite directions. So when we consider, for example, vectors, we will know more information than scalars, so therefore some quantities we would want to know as the vector, but some quantities can only be considered as naturally scalar. Now here we can see an object with both scalar and vector quantities associated with it. Now scalar quantities are represented by just a number and a unit, whilst the vector quantities are represented by a number and a unit, but also an arrow showing their direction. So if we look at these two particular vectors, the vectors on 1 and 2 are different, as vector 2 is larger than vector 1. We know this because the length of the arrow for vector 2 is longer than the length of the arrow for vector 1. Now it also shows us though that the vectors in 1 and 2 are similar, as they're acting in the same direction. We know this because the direction of the arrow for both 1 and 2 is in the same direction. Now we know that the length of the vector arrow must always be in scale with the size of the quantity. So for example, you could use a scale of 1 centimeter equals 1 Newton, and normally in most questions you can set the scale for yourself. So scalars must be represented by a number value with the unit, but vectors must be represented with a number value and an arrow. Now the direction of the arrow shows the direction of the vector, the length of the arrow shows the size of the vector. Now adding two scalars is very simple. It's the standard addition which you've carried out all the way through school. So for example, what is the total volume if volume 1 is 10 centimeters cubed and volume 2 is 20 centimeters cubed? Well, if it's scalars, you just add the two numbers together, so 10 plus 20 equals 30 centimeters cubed. But adding two vectors is more complicated, as you must consider direction as well as size. Now in physics, opposite directions are considered as negatives. Now it doesn't matter which direction is considered the negative, only that one of the two is. So you might consider upwards to be positive and downwards to be negative, or you could say that negative is upwards and positive is downwards. It doesn't matter as long as one value is a negative and one value is a positive. So what we know is if we give a value a plus or a minus, we must be considering a vector value. The only exception is temperature, as physicists messed this quantity up when we first understood what temperature was. So let's look at an example of adding two vectors. So in the following example on the screen, the overall vector is going to be 3 newtons, because we've got got 5 in one direction and 2 in another direction, we'll decide to call the 2 the negative value. So 5 plus negative 2 equals 3. So to find the overall vector, you add the vectors if they're in the same direction, but you subtract the vectors if they're in opposite directions. Now, when the name for an overall vector on an object is called the resultant vector, or in terms of forces, the resultant force. Now, if an object has a resultant force acting on it, it will accelerate. If an object has no resultant force acting on it, it will not accelerate. It will stay at the same speed. Now, this particular property is called inertia, and it's Newton's first law of physics, his first law of motion, which is a fundamental rule of the universe. But what happens if the vectors are not completely in opposite directions? Well, to add any two vectors, you've got to draw something called a scale diagram. Now, these diagrams accurately show the size and the direction of the overall vector. Now, remember, we know that resultant in physics means the overall or the observed. So you can't just add vectors. The resultant vector is in fact the straight line distance from the start of the diagram to the finish of the diagram. So to draw a scale diagram, first thing you've got to do is you've got to set a scale to your work. So for example, 1 square equals 1 Newton. You then draw the first vector with the correct length and direction. So say for example, our first vector is 8 newtons, we will draw that to 8 squares. Now you've got to draw the arrowhead in your vector as well. What you then do is you draw the second vector with the correct length and direction and place the tail of this vector at the head of the previous vector, which gives us the other name for our particular scale diagrams. They can sometimes be called the head to tail diagram because the head of one vector is touching the tail of the next vector. Now the resultant vector is from the tail of vector 1 to the head of vector 2. So remember, you should always be drawing in your arrowheads to your vectors, so you can draw this easily. You can then measure the length of the vector with the ruler, and you can measure the angle with the protractor. Now you've got to remember to convert the length back into a value by looking at your scale. Now again, remember, when given an angle, you've got to say where you start measuring your angle from, either the vertical or the horizontal. In most cases, it's easier to measure the angle from the vertical. So let's just clarify what you've got to do. To add vectors, you've got to draw a scale diagram. These diagrams accurately show the size and the direction of the overall vector. So to draw a scale diagram, you've got to set a scale to your work, draw the first vector with the correct length and direction, then draw the second vector with the correct length and direction, placing the tail of this vector at the head of the previous vector. You're then going to draw a resultant vector from the tail of vector 1 to the head of vector 2. You then measure the length of the vector with the ruler and the angle with the protractor, and remember to convert this with a scale. Now you might have realized that in the previous example, we have drawn a right angled triangle with our vectors. This means we could actually calculate the length of the resultant vector with the Pythagoras theorem and calculate the angle of the vector with trigonometry. Now this method is actually the A-level method because for GCSE examinations you've got to draw the scale diagram to get the full marks, but you can work out the resultant vector by using the equation that resultant vector squared is equal to vector 1 squared plus vector 2 squared, and the tan of the angle is equal to vector 2 over vector 1. But remember, this Pythagoras method can only be used if the two vectors are at right angles to each other. So we can use this example to work out both the resultant vector and the angle. So in this particular example, you can see we've worked out the resultant vector by doing the two values squared and added together. What we can then do is we can then square root that answer and work it through to get our resultant vector to be 14 newtons. What we can then do is say the tan of the angle is vector 2 over vector 1. So in this case it's 8 over 12, which equals 0.67. So our angle is then 34 degrees from the vertical. So what have we learned in today's lesson? We know that scalar quantities have a magnitude only, and that vector quantities have a magnitude and an associated direction. A vector quantity may be represented by an arrow, and the length of the arrow represents the magnitude, and the direction of the arrow shows the direction of the vector quantity. A number of forces acting on an object may be replaced by a single force that has the same effect as all the original forces acting together, and this single force is called the resultant force. Now you should be able to calculate the resultant of two forces that act in a straight line, and you should be able to describe examples of forces that act on isolated objects or systems, and use vector diagrams to illustrate the resolution of forces and determine the resultant of of two forces including both magnitude and directions with scale diagrams. So if we've been successful and we've learned in today's lesson, we should be able to describe the differences between scalar and vector quantities, add vector and scalar quantities, and finally draw vector diagrams for vectors where the size and the direction of the arrow represents the size and the direction of the vector. So I hope you've enjoyed today's lesson on scalars and vectors, which is part of the GCSE Combined Science topic of forces in the physics subject specification. Thank you very much for watching and have a lovely day.